So 7.4 vectors. All right, so a vector is a line segment with magnitude, which is the same thing as length, and direction, which is to say that a line just kind of goes off both directions. It doesn't have a length that goes on forever. This right here is a line. And it doesn't have a direction either. It goes in this direction here, and then it goes in this direction here. It goes in both directions. It doesn't go in any direction. A vector, on the other hand, starts in one place, and then it stops in another. So like it starts right here and then ends right here. So it has a set length. It is this long. It does not continue offward. It is this long here. And it has a direction. It is going this direction. So it's going off this way. So this right here would be a vector. The place where the vector starts, we call the initial point or the tail. And the point where it ends, we call the terminal point, or the tip, but I like to use the word head. But sometimes it's referred to as the tip of the vector, the head or the tip of the vector. So that's a vector, and that's its difference from a line. The only difference is this thing has no length because it goes off forever. This thing is just right here. That's its length. It's this long. And it has a place where it starts, a place where it ends, and it has a direction. It's going from here to here. There's a lot of things we can do with vectors. Geometrically, we can add vectors, we can subtract vectors, we can make multiples of vectors. So let's talk about adding vectors geometrically. When we add two vectors geometrically, so I have a vector here and a vector here, you're going to add them head to tail. So my first vector is v. Let me just copy and paste. Here's v right here. So it's starting at some point here, ends at some point here. And then the second vector, w, it gets added where I put the tail of w at the tip of v. So copy, paste. So the tail of w is at the tip of v, and then I end there. But this isn't the actual resulting vector, because if I added these together and I said, oh, this is the result. This is the vector that is a result of adding the two vectors. Well, this isn't a vector at all. This is just a weird shape here, right? So the vector that is actually the result comes from drawing from the tip of not the tip, it starts from the tail of where you started and goes to where you ended. So the head of the resulting vector is at the head of the end of this chain of command. So this vector right here would be v plus w. A vector can also be drawn negative. So a negative vector is simply going to be the same exact vector, but it goes the opposite direction. So hold on, paste. So I have my vector v. This is still the original vector v. If I come in here and erase some stuff, and I draw it in the opposite direction, this would be negative v, because it goes in the opposite direction of v, but it's the same length and it's the same, angle. So it's angled like this one's angled like that, and it just goes the opposite direction. We can use that idea of negative vectors to talk about how we can subtract vectors. So we're not actually subtracting vectors, we're adding a negative vector. So I have two vectors v and w, once again, and I'm going to look at doing v minus w. But as I'm pointing out over here, that's really going to be v plus negative w. So let me start by finding negative w. This is regular w. Oop. Let me just erase that arrowhead there. It goes in the opposite direction, so this is negative w. I'm going to start with v. Oops, I did not want to cut. I wanted to copy, paste. So I'm starting with v. We'll say v starts here, ends here. I don't think I left myself enough room, so let me move that. And then I'm adding negative w. Then just like we did before, we'll start at the very place where we started, so the tail of v, and go to the head of w. And this would be the vector v minus w, which is really just v plus negative w. So let's do an example where we're looking at a grid here. So on this grid, you can easily tell how far over it goes and how far up it goes, which makes it better than trying to freehand. And we're going to do two things. We're going to do v minus w, 2v plus 3w, and then 2v minus w plus u. All right, let's start with v minus w. So we already have w. Let me go ahead and draw negative w over here. Now notice that v goes down 2 blocks and over 2 blocks. We're just going to make it the same. It's going to go over 2, up 1. It's going to take up the same amount of space, but have the arrow on the other side. So this guy right here would be negative w. So we're starting with v. So v starts and then it goes up 2 and then right 3. So here is v. Then maybe I need to move this a little bit. Oh, and it's not going to let me. Hold on a sec. Sorry, I had to move it a little bit so that I had enough room here to put on w. So here's v. We're doing v plus negative w to do v minus w. So I'm taking negative w. Negative w starts here, and then it goes to the left 2 and up 2. So it starts here, left 2, up 2, ends here, negative w. And the vector we're actually interested in, maybe I'll make it in black so it stands out, goes from where you started to where you ended. This is the vector v minus w. All right, for part B, we need to do 2v. So just regular v would, let's see how much space I need to give myself. I'm going to give myself a lot of space here. Would start and it would go up 2 over 3. So this would be like one version of v. But if I wanted 2v, I would just need to do that twice. So I would actually make it this long. This would be 2v because it is twice as long, twice as wide. So this is 2v. 3w. All right, part B. Now, this is 2v. Regular v, let me start down just a tiny bit. Regular v would go up 2 to the right 3, and that would just be one version of v. 2v will just be putting 2 of these v's in a row. Essentially, 2v is the same thing as v plus v. So you're adding 2 vectors of v together. So I can just kind of erase those little arrows there. And this big arrow is 2v. The next thing we have is 3w. So this is w right here. I'm doing 3 versions of it. So this would be 1. This would be 2. And this would be 3. So this whole thing here would be 3w. The vector 2v plus 3w would be going from the tip, or from the tail to the tip. That whole vector, that black vector I've written in there, is 2v plus 3w. All right, finally, 2v minus w plus u. I'm going to need to start down kind of far here, so I'll start right here, should be fine. And I'm going to do 2v, which I've already done before. So up 2 over 3, that's going to be one of them. Up 2 over 3, that would be the next one. So that's 2v. Minus w. So here's negative w, so adding negative w. This is negative w. And then plus u. U is this guy right here, so he goes up 3 to the right 1. So starting right here, up 3, right 1. This guy is u. Our resulting vector starts down here at the tail, goes to the head, and this would be 2v minus w plus u. No, it's kind of tiny in there, but there's that. So while the geometric forms of vectors I think are a lot of fun, I think it's a lot of fun to do stuff geometrically, more frequently what you're going to be experiencing, especially if you go into calculus, if you go into calculus 3, I want to say, hold on. Yeah, Calc 3. So if you go into Calc 3, you're going to be seeing vectors, and if you go into physics, you're going to see a lot of vectors, but they might do it a little differently. Regardless, you're not going to be seeing geometry as frequently as you're going to be seeing algebra. So in general, you have a vector, and you have a place where you start. You then go over a certain amount, we'll call that amount A, and then you go up a certain amount, we'll call that amount B. Now, A is going to be positive if you're going right, and then it would be negative if you go left, which is the same as like our coordinate system. B is going to be positive if you go up, and negative if you go down. So we call A, we call that the horizontal component, and we call B the vertical component. So every vector has two components associated with it. One of them is a horizontal component, one of them is a vertical component. And the way that we write it in this form here. So I guess something I haven't pointed out in this video yet is that vectors are special. We write a little hook on the top of the vector. The hook on the top of the vector just means that it is a vector. On Alex, you'll notice that they're written in bold. So if you were a textbook, you could bold things, but it's a lot more effort for me to bold things than it is to just write a little hook over the top. So when you're handwriting, you typically just write the little hook over the top to denote that it's a vector. And then let me write here that A is the horizontal component. And B is the vertical component. You don't draw parentheses here. Vectors are special in that they use these angled brackets to denote that they are vectors. So the vector itself gets a little hook on the top to note that it's a vector, or it's written in bold. And then its component form has these little angled brackets to denote that it's not a point, but a bracket instead. So there's our component form of a vector. But what might be burning in your head right now is, well, what if we have 2 points in the plane and we want to figure out how to write that vector in component form? I'm sure that's what you're thinking. So for instance, let's say we have this point, we start here at 1, 1, and we end here at 8, negative 2. This is the vector v, and we wanted to write it in its component form, not just draw it. Well, I mean, we can do this, right? We know what its vertical and horizontal components are going to be. So for its horizontal components, it starts here, it goes over 1, 2, 3, 4, 5, 6, 7. So its horizontal component is 7 because we went to the right, so it's positive. And then it starts here and it goes down 1, 2, 3 units. So its vertical component is negative 3 because we went down 3 units. So we can say that vector v is in component form 7, negative 3. This is saying that it goes right 7 units and then down 3 units, and that's where it ends. And let me end my parenthesis there, which is great. But there has to be a faster way to do this, right? We shouldn't have to write a vector in the plane every time we want to figure out what its component form is. And indeed, there is a way to do this. So let's look at the horizontal component first. We began at 1 and ended at 8. 7 is the distance. If we come in here and let's kind of make it a bit more generic, let's say that it starts at the point x1, y1 and ends at the point x2, y2. It looks like 7 is the difference from where it ended and where it began, right? 8 minus 1 is 7. And it would make sense that if you take where it ends and you subtract where it began, that you would get the difference in between, right? The difference between here and here is this number minus this number, and it gives you the in-between. Same thing with the vertical components. Now, it looks a little bit different here because it's going to end up being negative. If we did 1 minus negative 2, we would get positive 3, because 1 minus negative 2 would be positive 3. And it's supposed to be negative 3. So instead, we're taking where it ends, just like we did with the horizontal component. 8 minus 1 gave us this positive 7 here. You do the same thing. Where does it end? It ends at negative 2. Where did it begin? It begins at 1. Negative 2 minus 1 would give you that negative 3 there. That'll give you the distance between those two. So we can formalize this. And here I have it already written out here. We can formalize this and say that if a vector begins at one point and ends at another, that it can be written in its component form as the difference between the x components and the difference between the y components, so the horizontal and the vertical. So x2 minus x1, y2 minus y1. Let's go ahead and do a few examples with those. All right, so we have a vector u. It has initial point negative 1, 2. That's right here. And terminal point 4, 6. So over 4 up 6. This is my vector here. And it's the vector u, so I'll just label it. We want to write this vector in component form. So our initial point is going to be our x1, y1, and our terminal point will be our x2, y2. Our formula says that our vector u should be equal to the difference in the x component, and then different for the difference in the y components. So x2 is 4, minus x1 is negative 1, comma, y2 is 6, minus y1, which is 2. 4 minus negative 1 is the same as 4 plus 1, which is 5. 6 minus 2 is 4. So the answer should be 5, 4. Let's go ahead and verify that using our picture over here. So we're starting here. We're going over 1, 2, 3, 4, 5. So 5 for the horizontal, which is correct. And then we go up 1, 2, 3, 4. Up 4, which is the horizontal component. So that makes sense. It works. Let's do one more. Once again, we have a vector. This time it's w. It has initial point negative 4, negative 3. And terminal point negative 5, positive 2. So this will be the vector w. Now, you're not always going to draw these pictures. I'm just trying to show you and claim to you that this does work out. So w, the formula is equal to x2 minus x1, comma, y2 minus y1. This is x1, y1. This is x2, y2. So x2 is negative 5 minus negative 4, comma, 2 minus negative 3. So really this is negative 5 plus 4. This is 2 plus 3. So I'm getting negative 1, positive 5. So the horizontal part is negative 1, the horizontal component is negative 1, and the vertical component is 5. So it should be going, what this is telling me left 1, it's left because it's negative, and up 5 from my original starting point. So I started here, and I go left 1, that looks right, and then up, let's see, 1, 2, 3, 4, 5. So negative 1 here, positive 5 here because I went up. Then that's our answer. So negative 1, comma 5. So now that we have this component form of the vector, we talked about adding vectors geometrically, we talked about negative vectors, we talked about subtracting vectors, and we even talked about multiples of vectors, right? 2v, 3w, we talked about all those. And if we can do it geometrically, it would make sense that we can do it out with the component form as well. And we can. So let's say we have two vectors, v and w. V has horizontal component a1, vertical component b1. W has horizontal component a2 and vertical component b2. And then c will be a constant. And remember, a constant, this is just a number. So c is a constant, which means it's just a number like 5 or 4. It's a number that's not changing. So if we're doing this, we have, where's my pointer? If we're doing v plus w, we have these component forms up here. So this would be the same thing as a1 comma b1 plus a2 comma b2. The way that you add these together is simply adding their components together. So the horizontal components get added together and the vertical components get added together. So it's a1 plus a2 comma b1 plus b2. Just adding the components together. For subtraction, it works the same way. So if you have a1 comma b1 minus a2 comma b2, you just subtract. So it would be a1 minus a2 comma b1 minus b2. Finally, if you have a constant out front, so there's some constant here, and you have this vector a1 comma b1, the way that this works is it just gets distributed. So the c gets distributed not just to one, but to both. So you would have ca1 comma cb1. And I want to take a quick look back at our picture where we did this. And so this guy right here is v2, 2v. This vector right here, if we wrote him geometric in component form, he goes to the right 1, 2, 3. So this is 3, and then he goes up 2. So this is the vector 3, 2. Over here, this is 2v. So we go up 1, 2, 3, 4, 4. We go up 4. And then we're going to the, we're not doing the vertical first. Hold on a second. We go up 4, so that should be the vertical component. And then for the horizontal component, we go 1, 2, 3, 4, 5, 6. So 2v is 6 comma 4. V is 3 comma 2. Look at how both of those components are doubled. So 3 turns into 6, 2 turns into 4. That would mean that if you have 2v, so 2 times the vector 3 comma 2, that this is 2 times 3 and then 2 times 2. And that's how you're getting that 6 comma 4. So this works out geometrically. It means the same thing geometrically that it does when you're doing it with components. You're just multiplying each component by whatever constant you have. Let's use that in an example. So we're given 3 different vectors here, and we're going to find r plus t, t minus w, and then 5w. So let's do r plus t first. All right. So r is 7 comma negative 3, and t is negative 2 comma 8. We're going to add the components together. So 7 plus negative 2, comma, negative 3 plus 8. So we added these two together here and added these two together here in the vertical component position. 7 plus negative 2 is 5, and negative 3 plus 8 is 5. So we have the vector 5 comma 5. And that's r plus t. Let's do t minus w. So our vector t is negative 2, 8, and there's a minus sign, and then w is negative 5 comma negative 4. So once again, when you were doing this geometrically, when you went to subtract vectors, you had to like make negative w in order to do that. You don't have to do that in the component form. The component form, you can simply just subtract this minus this, this minus this. It's almost exactly what you think would happen, which doesn't always happen in math. So negative 2 minus negative 5, 8 minus negative 4. No, negative 2 plus 5 is 3. 8 minus negative 4, that's 8 plus 4, which is 12. So we have the vector 3 comma 12. Finally, we have parts, not really part C, but we have this 5W here. We'll call it part C. So 5W is taking 5 and multiplying it by the vector W, negative 5 minus 4. So you take the 5 and we're distributing it inward. So we have 5 times negative 5, comma, 5 times negative 4. And that gives us negative 25, comma, negative 20. And that's that. Now we can make it a little crazier, and we could, try adding multiples of each vector to another multiple of another. And it's not going to be that bad. So negative 5a plus 3b. So we have negative 5 times the vector a, so that's 9 comma negative 4, plus 3 times the vector b, which is negative 6 comma 0. We're going to distribute first. Negative 5 times 9 is negative 45. Negative 5 times negative 4 is 20. 3 times negative 6 is negative 18. And 3 times 0 is 0. Now that we've done that constant, we've distributed the constant, we can go ahead and just add straight. So our horizontal components are added together and our vertical components are added together. So we have negative 45 plus 18. Oop, not plus 18. It's plus negative 18, comma, 20 plus 0. Negative 45 plus negative 18 is the same as negative 45 minus 18, which is negative 63. 20 plus 0 is 20. And that's our final answer. So manipulating vectors when they're in their component form is actually pretty straightforward and almost what you would hope for if you were trying to make up your own system here. Let's talk about some other properties that vectors have. So at the very beginning, I said that vectors have a magnitude, which is the same thing as length, and they have a direction. And we've just kind of inherently assumed that as we've gone through these examples. Yes, this has a direction. Yes, it has a direction. We don't really talk much about what the direction is. Yes, this has a length. Yes, this has a length, but what is the length? So let's talk a little bit about that. We'll start by talking about the magnitude. So the magnitude, i.e. the length of a vector, is given by this formula. Now, Alex doesn't use this notation very frequently, but you will see this notation a lot in math. It's like an absolute value sign, but it's two of them. So when you have those two absolute value signs, that's talking about the magnitude of something, which is the length of something. And you see that all it is taking the square root of the two components squared and then add together. But as a good mathematician, you should ask yourself, why? Why is that the case? Well, let's say we have this vector v, right? And it has, let's use red here, horizontal component A, vertical component B. Notice when I draw it like this that it makes a nice right triangle. We could say that we're trying to solve for the length of this side here, which happens to be the hypotenuse of our triangle. We know that a squared plus b squared is equal to c squared by the Pythagorean theorem. We're trying to solve for c, so we're taking the square root on both sides. Now, technically, when you take the square root on both sides, you should be putting a plus or minus there. However, because we're not actually solving for a number, we're solving for a side length. Side lengths have to be positive. So a length of something, you don't say that you're negative 5'5", right? You're 5'5", that's your height. So heights and lengths, those are all positive numbers. So we're not going to take the negative, we're just going to take the positive, and we can say that c is equal to the square root of a squared plus b squared. And that's where that's coming from. Let's use it in an example. So we have this vector, 6, negative 3, and we want to find the magnitude of it. We want to find the length of it. So we're going to say that a is equal to 6, b is equal to negative 3, and the formula we were given is that the magnitude is equal to the square root of a squared plus b squared. Now, here's a fun thing. When you move into 3 dimensions, so you can have vectors that have actually infinitely many components, but you can have as many components as you want. This would be a 3-dimensional vector, so this would be something that you could, it would be like a string running through your living room. It would have a third component, which would be the z component, which brings it out into outer space, into our living world. If you were trying to find the magnitude of something like this is just a side tangent, but you can't stop me because it's on a video. Its magnitude would be a squared plus b squared plus c squared. And you could do that for as many components as you had. That's just something fun. Can't stop me. I'm unstoppable. All right, cool. So back to the magnitude of this particular vector. It's a squared, so 6 squared, plus, and this is really important, you need to square the negative part of this. If you put it into your calculator as 6 squared plus negative 3 squared, the way your calculator is going to read this, it's going to say 6 squared minus 3 squared, and that's not what you want there, so be very careful. 6 squared is 36, 3 squared is 9, and you get the square root of 45. Now, Alex is going to want your answer in a simplified radical form. So as a review of simplified radical form, you want to determine if there are any numbers that divide 45 that are square numbers. Square numbers are numbers that result from squaring a number. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. So these are the first 10 squared numbers. I know that 9 divides 45, so I can rewrite the square root of 45 as the square root of 9 times 5. I can then distribute the radical over both of these. And then the square root of 9 is 3, so 3 square root 5. That is the magnitude of vector v. Let's make it a little more fun. So we have two vectors here. We're going to find the magnitudes of r and of w, and then we're going to find the magnitude of when they're added together. So let's start with the magnitude of r. So we'll be doing a squared plus b squared, which is 1 plus 4, the square root of 1 plus 4, so square root of 5. So I can say that the magnitude of r is equal to the square root of 5. For w, we're taking the square root of the horizontal component squared plus the vertical component squared. So 9 plus 16, that's square root of 25, which is 5. So the magnitude of the vector w is 5. So here comes the really, really big question. If the magnitude of r is square root 5 and the magnitude of w is 5, will the magnitude of the two vectors being added together just be the magnitudes of each individual vector added together? Let's look at this geometrically first. So the question we're really asking is the length of this guy plus the length of this guy equal to the length of this guy? And I think it's a little easy right here to say, well, no, that's probably not true. This looks like this should be much longer. And you'd be right. There are situations in which they are equal. For instance, if you added v twice, if you did v plus v, that would mean that the magnitude of the vector v plus v would be the same. But in other situations, most situations, that's not going to be correct. Oops. So up here, let's go ahead and do r plus w. So that's 1, 2 plus negative 3, 4. 1 plus negative 3 is negative 2. 2 plus 4 is 6. So that's our r plus w vector. Oops, not a bracket, square root. So we're doing negative 2 squared plus 6 squared. That's 4 plus 36, which is the square root of 40. This can be simplified, right? Because we know that 4 divides 40 and 4 is a square number. So this will be 2 square root 10, which is approximately, let's pull out my calculator here, 2 square root 10. That's going to be approximately 6.32. Whereas if you added together these guys here, if you did the square root of 5 plus 5, this is going to be an approximate number here. This would be 7.24-ish. So this magnitude would be greater than this magnitude. That's all for me to say that, let's just write this here. You can't just find the magnitude of two vectors being added together by adding the two magnitudes together. You have to find the brand new vector and find its magnitude instead. There's actually a very frequently used property in math, the triangle inequality, that talks exactly about this, about the fact that this number right here, when you add these two together, is going to always be the same or less than the sum of these two added together. So, fun fact there. So just one last thing to talk about now. Let's talk about, okay, we have a vector and we know an angle here. We know this angle that's created, this acute angle that's created, and we know the magnitude of this. So we know how long this guy is and we know this angle. Can we find its component form? Can we find A and B? Sorry, A is this distance, B is this distance. And we can do that. So let me just draw a triangle real quick. We know that this side length is magnitude V. We know this distance is A, this distance is B, and we know this angle is theta. Well, we can say that cosine of theta, that's adjacent, so A over hypotenuse, which is magnitude V, we can say that cosine theta is equal to A over the magnitude of V. And by multiplying both sides by that denominator, we could get that A is equal to the magnitude of V cosine theta. If we use sine theta instead, that's opposite, which is B over hypotenuse, which is the magnitude of V. And we could say that B is equal to the magnitude of V sine theta. Thus, that whole vector, let me kind of move some of this. Move all that up. Thus, the vector V is equal to the magnitude of V cosine theta, comma, magnitude of V sine theta. Which, if you wanted to be real fancy, you could actually pull that magnitude V out front and do cosine theta, comma, sine theta. But either of those will work. So having that angle can help us find the vertical and horizontal components. So let's do an example of that. So here we go. We have this picture here. We know this angle and we know this magnitude. Now, what's going to really help is determining whether things should be positive or negative first based upon the direction of this vector. So we know that it goes down and then right? Or you could say right and then down. But we know that it goes down, which means its vertical component should be negative because it goes down. And then its horizontal component should be positive because it goes right. This is really important because when you do your trigonometry here, you're not going to end up with the right signs always, so it's important to do this. All right, so this distance over here, this will be A. This distance is B. We know that A, the vertical distance, should be magnitude V cosine of theta. This guy right here is the magnitude of V. We're just going to call this vector V. So 25 cosine of 54 degrees. You're gonna have to plug that in your calculator. And you get approximately 14.69. And then plugging the other one in, so B, our vertical component, that's going to be 25 sine of 54 degrees. So plugging that in, you get 20.23. And we already put our signs here, so let me just make it nicer. This would be 14.69, comma, negative 20.23. And just double checking, this is positive, right? Because it does go to the right, so it should be positive. This guy is negative because he goes down. And there you go, that's calculating those components. Let's do another example. So I'm gonna kind of set up the vector just like I did before. And looking here, it starts and then it goes to the left. So if it's going to the left, that means your horizontal component is going to be negative because it's going to the left. And then we also go down. This is A, this is B. We go down, which is also negative. All right, so for A, that's the magnitude of the vector, cosine of theta. So the magnitude of the vector is 89, cosine of 37 degrees. In my calculator, I plug that in and I get approximately 71.08. And then for B, that's the magnitude of the vector sine theta. So 89 sine of 37 degrees. And I get 53.56. So if I just rewrite this a little nicer, my vector, the horizontal component is negative 71.08, and the horizontal component is negative 71.08, and the vertical component is negative 53.56. And there you go. So just the important thing with these ones, just make sure that you are putting the right signs in. That's going to be the important thing. You have the formulas. It's just a matter of remember that if it goes down or left, that those components will be negative. So just two more examples to do. This one right here is a little bit different. So here we have where's my pointer? Here we have a picture. So we want to find the magnitude of the vector given below and the measure in degrees of this acute angle theta formed by the vector and the x-axis. So it's a little bit easier here if we draw this as a triangle. This distance right here, that's going to be 3, right? This is 1, 2, 3. And we could call it negative 3 if we wanted, but notice here that we're not finding the components of the vector. What we could, we could say that this is the vector v and it has the horizontal component negative 3, but that's not going to be as important since we're just finding the magnitude and this angle here. So you could call it positive 3 and b just as fine. This distance here, 1, 2, 3, 4, 5, so it goes up 5. So the magnitude of this vector would be the square root of negative 3 squared plus 5 squared. So that's 9 plus 25, which is the square root of 34. And that doesn't simplify anymore, so that would be its magnitude. Now, finding the angle, I'm going to draw this triangle here, but I'm not going to make anything negative. I'm just going to leave everything positive and pretend it's just a good old regular triangle, and I'm finding this acute angle theta here. Well, according to this triangle, I have an adjacent and an opposite side. So adjacent side is 3, the opposite side is 5, and adjacent and opposite, that sounds like a tangent situation. So tangent of theta is equal to opposite over adjacent. This is just a positive 3 I have here. So to find theta, taking tan inverse on both sides, theta is equal to tan inverse of 5/3. So on my calculator, I'm doing tan inverse of 5 divided by 3, and I get approximately 59.04 degrees. So theta is approximately 59.04 degrees. So you can see here where it wasn't really necessary to find this component. This negative really didn't help us in this particular problem because in both situations, the negative doesn't matter. In this triangle, it doesn't matter in finding theta. And over here, it didn't matter because for finding the magnitude, because you just end up squaring it anyway. So let's use that and do a different one here. Let's do this guy, find its magnitude and the acute angle theta. So this distance right here is 5. This distance right here is 6. So we have that the magnitude of this vector is equal to 5 squared plus 6 squared. So that's 25 plus 36. Adding those together, you're going to get the square root of 61. And I don't believe, nope, that does not simplify at all. So there's our magnitude. That's a V, even though it looks like an R, it's a V. For finding theta, we have this triangle. Sometimes it helps to just not have it written on the grid. We have this triangle, this is a 5, this is a 6. So the opposite side for theta is 6, the adjacent side is 5. Tangent, or opposite and adjacent, that's a tangent situation. So opposite over adjacent, taking tan inverse on both sides. Theta is equal to tan inverse of 6 over 5. So tan inverse 6 over 5. That's 50.19 degrees. So theta is approximately 50.19 degrees. And as simple as that. So, you know, you're going to be doing a bunch of different things in this section. There's a bunch of different ways that vectors can be represented, and it's important to know all of them. Vectors won't become super important again in your life until you either take physics or you take calculus 3, so it will be some time before you see them again, but they will come back and they will be important. And maybe since I'm looking at this vector right here, and because I did it with this guy over here, let's write what this vector would be in its component form. So for the horizontal component, it moved to the left, which means it should be negative because it went left. And then it went down as well, so the vertical component should be negative as well. So it didn't ask for that on this problem, but you know, it's fun to write it down. So that's all I have to say about vectors. Hopefully that all made sense. Hopefully you're having a good time learning about vectors. I think it's kind of fun. It's a nice change from all the other stuff we're doing. Hope you have a great day, and I will see you in another video.